ME347, Example 7. Drag for uniform flow over a flat plate with turbulent and mixed or transitional boundary layers. A hydrofoil with a length of 1.2 feet and a width of 6 feet is moving through seawater at a velocity of 40 feet per second. Note that this is about half the size of a boogie board moving sideways through water at a high speed. Estimate the drag force for A, a rough leading edge, and B, a smooth leading edge. For this problem, we will assume steady, incompressible flow of a Newtonian fluid. Also, that the flow has uniform velocity with negligible end effects. Thus, it can be modeled as a two-dimensional boundary layer. Finally, we assume a smooth, flat plate with a rough leading edge that trips the boundary layer to turbulent over the entire plate for part A, and a smooth leading edge that allows the boundary layer to begin as laminar and then trip to turbulent at a critical Reynolds number of 500,000 for part B. Before we begin our calculations for parts A and B, let us check the Reynolds number at the end of the plate. We find that it is over 4 million, so the flow is likely to have transitioned to turbulent at some location along the hydrofoil. We then also calculate the location for transition for the boundary layer based on our critical Reynolds number and get 1.65 inches. This is about 10% of the length of the hydrofoil aligned with the flow. For parts A and B, because we want to know the total drag for the surface, we begin by calculating the drag coefficient for friction and then use that to calculate the actual drag due to friction. For part A, for our rough leading edge, we use a correlation for turbulent flow over the entire plate. Then, using the properties for seawater and an area that includes both sides of the hydrofoil, we get a force of about 80 pounds force. For part B, for a smooth leading edge, we repeat the calculation using a correlation that corresponds to a flow that starts as laminar and then transitions to turbulent at a Reynolds number of 500,000. Note that the first term on the right is the same as from part A for turbulent flow, and that we subtract the second term, which accounts for the laminar flow over the first 10% of the hydrofoil. Based on these calculations, we see that the drag drops by about 19% to 71 pounds force. Finally, let us look at some figures to compare laminar and turbulent flow. The figure on the left shows how the boundary layer thickness changes with distance along the plate. We see that the turbulent boundary layer is much thicker than the laminar. The plot on the right compares the velocity profiles at the end of the airfoil if the profile stayed laminar to the case where it tripped to turbulent. Note that the turbulent profile is obtained by time averaging instantaneous velocities, which will fluctuate significantly. In addition to confirming that the turbulent boundary layer is much thicker, we also see that the velocity gradient at the wall is much steeper for the turbulent flow. Both of these differences are due to enhanced turbulent mixing, which pushes more high-speed flow towards the wall, resulting in higher shear stresses, and out into the free stream flow, resulting in a thicker boundary layer.